Hey there folks, I'm going to be talking to you about limiting reactants and percent yield. So I'm making a couple assumptions here that number one, you've already gone over stoichiometry and you can convert grams to moles and moles to grams, okay, using dimensional analysis. So making sure that you show how your units are changing from one unit to another. I'm also making a major assumption that you're able to use a balanced equation to get the mole ratio appropriately. So again, go back, review stoichiometry before you do this, okay? So as the name implies, limiting reactant, we're talking about something that limits the amount of product that is produced. So in a chemical reaction, there's always going to be something that's going to limit us in the amount of product that we produce. And so that is what we call the limiting reactant. All right, so what I'm going to do is I'm going to show you how it is that a problem in stoichiometry slightly differs, and we're going to be looking at the idea of a limiting reactant. So here's an example. We've got sodium reacting with oxygen to produce sodium oxide, okay? And it says you begin with 46 grams. So the key is that it begins with 46 grams of sodium and 32 grams of oxygen. And the question is how much sodium oxide would be produced. Now, you're going to say, well, how is this any different than any other stoichiometry problem that we've dealt with? Well, if you notice, we've been given two different masses, okay? One for each one of the reactants. So we don't know which one is going to limit us in the production of the product. And it doesn't always have to be the mass that is smaller. It could be the mass that is larger, depending upon the mole ratio. So this is why we go through the calculations to do this, okay? So the first thing we have to do is to be able to determine which reactant is limiting us in the production of the product. And then whichever one produces the least amount of the product would be considered the limiting reactant. Okay, so I'm going to show you how it is that we do this calculation. So this was the problem. The question is how much sodium oxide will be produced. Okay, so what we're going to do is we're going to set up not one calculation but two calculations here. We're first going to figure out based upon starting with our 46 grams of sodium. All right, we're going to figure out how many grams of sodium oxide this would produce. Okay, so the first thing we're going to need to do is convert our grams of sodium into moles of sodium. All right, so that requires the molar mass, which you get from the periodic table. So 23 grams of sodium, there is 1 mole of sodium. Okay. From there, we can now use our mole ratio. And in our mole ratio, we've got for every 4 moles of sodium, there are 2 moles of sodium oxide produced. Now, I could stop here and solve for moles, but you know, it's up to what you want to do. This one particularly doesn't say, it just asks how much sodium oxide will be produced. It doesn't say that it needs to be in moles. It doesn't need to say that it's in grams. I'm just going to go ahead and solve for in grams. Okay, so then we're going to use our molar mass. So in 1 mole of sodium oxide, that would be 62 grams of sodium oxide. Okay, and that's the molar mass of that. All right. For the next part, we're going to set it up so that we have 32 grams of oxygen. Okay, so in 32 grams of oxygen, there's 1 mole of oxygen. Again, I'm using the molar mass. And then I'm going to use my mole ratio. So for every 1 mole of oxygen, I'm going to produce 2 moles of sodium oxide. And then finally, I will use the molar mass of sodium oxide, which is still going to be 62 grams of sodium oxide for every 1 mole. So if I do the math here, this comes out to be, if I'm doing this correctly, 62 grams of sodium oxide that we're going to produce, because 46 divided by 23 is 2. 2 times 2 is 4. 4 divided by 4 is 1. And 1 times 62 would give me 62 grams, because the grams of sodium cancel out, the moles of sodium cancel out, and the moles of sodium oxide cancel out. Here on the next problem, we've got 32 divided by 32, which would be a value of 1. and 1 times 2 is 2. And so 2 times our 62 would give us a value of, let's see, 2 times 62, so that would be 124 grams of sodium oxide. Okay, so those are our 2 possible answers. Now the question is, which one's correct? Well, here's the thing. We are limited in our production of our product, which means that whichever one produces the least amount is the correct answer. So what that means, ladies and gentlemen, is that this is the maximum amount of sodium oxide that I can produce, 62 grams of sodium oxide. But you're going, but wait, here's the thing. You've got 124 grams of sodium oxide you can produce with the 32 grams of oxygen. But the issue is I'm going to run out of sodium before I run out of oxygen. And you're going to say, well, how is it possible that I could run out of sodium when in this whole reaction? Well, and that comes down to that ratio of for every 4 moles of sodium, you're going to produce 2 moles of sodium oxide, as opposed to for every 1 mole of oxygen, you're going to produce 2 moles of sodium oxide. So the mole amounts play a key role, as well as the mole ratio. So our answer here, ladies and gentlemen, is 62 grams of sodium oxide is what I can produce. Okay. Now, a couple other side questions that I could possibly ask, such as which reactant is limiting reactant? Well, as we discussed, the one that's limiting me is the sodium. Okay, the sodium is limiting me in my production, and the reason I know this is because it produces the least amount of the product. Okay, that's how I know. All right. Now, the question is, which substance is in excess? Meaning, which one's going to have leftovers? And the leftovers we're going to have remaining in excess will be our oxygen. Our O2 is going to be in excess. Now, you notice that I have this question. It asks, how much? So how do we figure how much is going to be remaining? Couple different ways. I think one of the easiest ways to do that is just start with our limiting reactant and figure out how much of the oxygen we actually use in the chemical reaction. Use as opposed to what we have. So we're going to compare what we have versus what we used. And that will determine how much is left over. Okay? So I'm going to start with our limiting reactant. And in our particular question, the limiting reactant was our grams of sodium, okay? So our 46 grams of sodium, all right? In every 23 grams of sodium, there's 1 mole of sodium, okay? And in every, based upon our balanced equation, for every 4 moles of sodium, there's going to be 1 mole of oxygen. And I'm going to convert it into mass. And the reason I'm doing that is because we were given a mass. And so for every 1 mole of oxygen, there are 32 grams of oxygen. That's the molar mass. So the grams will cancel out for the sodium. The moles of sodium will cancel out. And the moles of oxygen will cancel out. So if I do my math here, I've got 2, it's going to be half, so it's going to be 16 grams of oxygen. You're going to say, okay, 16 grams of oxygen, what does that mean? This is 16 grams of oxygen that are being used. Okay, 16 grams of oxygen that are being used. Well, how much did we start with? Well, from the original problem, we started with 32 grams of oxygen, not Q. O2 is what we have, minus our 16 grams of oxygen that we, used. And so that means we have 16 grams of oxygen that are in excess, meaning leftover. Okay? Now, that leads us to something that scientists like to do, which is we like to determine how well we were able to prepare a product. And one of the ways that we test ourselves is by doing what's called percent yield. Basically, what we're trying to do is give ourselves a grade as to how well we produced our product. Now, I'm hoping you all agree that the max amount of a product that we should get is 100% of the product. But a lot of times there are side reactions that take place that we might lose mass in the chemical reaction upon filtering or things like that. So we like to determine and compare and actually figure it out. So there's an equation for it, and the equation is right here, where we have the actual mass, which is done experimentally, okay? And we have the theoretical mass, which is, for our purposes, it's calculated, meaning in a perfect world, that's what we should get. But in an actual world, meaning doing the experiment, this is what we got, okay? So if we are to use this, so let's say, for example, after performing the experiment, we actually collected only 40 grams of sodium oxide, the question is, what is the percent yield of that reaction? Well, this right here, the 40 grams of sodium oxide, is my actual, okay? And you're going to say, well, what's my theoretical? Well, that's what we figured out earlier, is that was the 46 grams of sodium oxide that we would produce. So I'm going to take my 40 grams, oh, I'm having a real hard time with this pen today, 40 grams of my sodium oxide, which is what I actually got, divided by what theoretically I should get, which is 46 grams of sodium oxide. And then I'm going to multiply that by 100. And when I do that, I can actually calculate that out and get a percentage. So I'm going to take my 40 divided by 46, multiply that by 100, and I end up with a value of 86.95 blah blah blah, which really comes down to about 87%. And basically what it's saying is that I got 87% of the product. It doesn't tell me purity, but it at least gives me an idea of how well I was able to collect and produce my product, okay? What we're trying to look for is 95% or better is what we're trying for. But a lot of times side reactions take place. And this is a great way of testing ourselves on it. All right, hope that was helpful.